Okay, so I've got to open up here with a few announcements. We have Lab 2 is due on Monday. And by due, we mean we want you to submit it, your helloworld.c on Dropbox by Monday. And then you can demo it that week, next week. So Wednesday and Thursday, March 2nd and 3rd. Is that right? I think so, yeah. So submit it by Monday and then demo it sometime in lab to either Philip or me next week. We'll have a midterm exam next week, and I'm just going to use the same format basically as the quizzes. So it'll be on Moodle, and you could take it anytime next week. So between midnight Monday, February 28th, and 11:59 on Friday, March 4th. So anytime next week you can take it. It'll be a little different from, it'll be the same as the quizzes in the sense that it's open book and open notes and open internet, but there'll be one attempt instead of two, and you have a 75-minute time limit from the time you start taking it. So it will cover everything we've covered up until this point, specifically bit manipulation, program I/O, interrupts, pulse width modulation, protocols, SPI, squared C, UART, and JTAG, and basic CAD tool questions from the lab, Quartus and Platform Designer. I will use next Monday's class, February 28th, as a review. So it's an optional review. You don't have to come if you don't want to, but I'll just be going over topics that will be covered on the exam, and I'll answer any questions you have. I'll also take that time to review quiz 3, which was due yesterday. So I'm going to defer. Normally I review the quizzes in class, but I'll just wait till the review to do that since quiz 3 covers stuff that will be on the exam. Quiz 4 will go online tonight based on how much material I cover today, and it'll be a short one. I don't want to, just so you know, it doesn't distract you from studying for the exam. Okay, any questions? Yes?
So for next week's lab, is it just demos, or are we going to have another lab? I haven't decided yet. I'm leaning towards just doing demos and then waiting to the following week to assign the lab. I don't really want to do that, but I think it'll work. I think it'll be easiest that way. Yeah, okay. Yeah, we'll just do demos then next week, because we'll probably need all the time for the demos anyway. So. Okay, thank you.
Okay, sounds good. Okay, so the next topic is hardware description language. If any of you took 611, you already know quite a bit about this. I've been introducing little bits of it into this course. And of course, you've already seen a little bit of hardware description language while working in the lab. I'm going to try to get through this. I'm going to try to be concise here. But in the next lab, we're going to try to combine, for the first time, this is kind of experimental, but the idea is that we want to have you design one of those IP modules that you add in Platform Designer. So you can design hardware that you can put in and then have the NEOS processor communicate with it. So that's the plan for the next lab. So HDL stands for Hardware Description Language, and there are the two most popular ones are VHDL and Verilog. VHDL stands for VISIC HDL, and VISIC is also an acronym that stands for a Very High Speed Integrated Circuit. I don't know what Verilog stands for, but both were developed in the 80s. VHDL was the first, and it was developed by the Department of Defense as a way to be able to convey accurate functional descriptions of parts to electric contractors that were supplying, chips for military equipment. Verilog was developed in the private sector a little later. I used to teach VHDL in this class, but then I switched to Verilog because it seems like it's becoming more popular. But in general, once you know one, it's very easy to learn the other. They're very similar. But what is hardware description language? So it's a high-level language that allows you to design hardware. And so it sits at a level of abstraction which allows you to define hardware behaviors, and then you use a CAD tool to convert those behaviors into circuits
And there's some flexibility for the CAD tool. It leaves enough flexibility for the CAD tool to decide how to map those behaviors to whatever the underlying technology is. So if you're designing an ASIC, like a chip, if you're taping out a chip, you can do that, or you can target an FPGA. The challenging thing, now you might think, oh, this is just another high-level language. All right, we know Python, we know C, we know Java, we're just learning another one. This is actually different in the sense that the other languages you've learned have sequential semantics, meaning that at any one time the computer can be considered to be executing a single line of code somewhere, and the lines of code are ordered. But in HDL, it has concurrent semantics, meaning that every line of code executes simultaneously because you're describing hardware, and hardware works that way. Does that make sense? So that's the main difference, and that's what makes it a little hard to learn. So both VHDL and Verilog and every other HDL is designed around this notion of a design hierarchy. So you design modules, and then you create new modules by building together existing modules. Right? So this creates a hierarchy where, for example, a CPU might be comprised internally of multiple processors, and each processor is comprised internally from functional units and a register file, and the functional unit is comprised internally of various pieces, and so you have this hierarchy. So this allows you to manage the complexity of a large-scale digital logic circuit. You guys probably know that modern CPUs have about 10 billion transistors, so how could anyone possibly design such a huge thing? And the answer is because it's all designed with this hierarchy. It's all these kind of reusable modules. And not only that, but there's this notion of regularity. Regularity, which is another word for reuse. The idea is that you design common submodules, and then you kind of use them multiple times. So you get a lot of mileage out of commonly used modules. Like, for example, down here I've got full adders, for instance, or adders in general are used a lot. And then like floating point functional units might be used a lot. So when you look at a modern processor and you say, well, who designed 10 billion transistors? Well, you got to understand that a lot of that is sort of copied and pasted within this design hierarchy. Okay, now why am I harping on this so much? Because when you look at a HDL file, it becomes obvious that the notion of hierarchy and regularity is kind of built into the design syntax. Because if you look at any HDL library, you see each file is a module. And the module starts out with top-level pins that form the interface to whoever is instantiating that module. And then whatever's inside that module is kind of like the guts, or what's under the hood, how it works internally. So you guys have already actually used one of these, except I just gave it to you instead of had you write it. This is the top-level module that you're using in lab now, which is called lights.sv. And it has this syntax. So, obviously I gave that to you, but moving forward, I want to be able to hopefully teach enough of this to you guys so you can write it on your own. So the way this works is you've got a module line that's usually the first line, although sometimes you have, header comments or include files like you would in a C++. But you start out with this module line, and then you give a name for the module. And then you have a port list, which are the inputs and outputs. So anyone who uses this module, these are the ways that it can connect inputs and outputs to it from the design that uses this module, right? So you can kind of think of this as the interface. And then notice that there's some strange, I like to point out the odd syntax things that the Verilog has. So notice that there's a semicolon here after the module line. This is all one statement. Even though I've split it onto 4 lines. But there's a semicolon here, and at the end, you end it not with a brace, but with the keyword end module with no semicolon. And then everything in between there is the hardware that's inside that module. And of course, that's the hardware that would be replicated if you instance multiple copies of this module, which is how chips get so complex. Inside the module line, you have inputs and outputs with names. So I've got an input A, B, and C, and an output Y. The type, obviously input and output comes first for each of these guys. The type is logic. Logic is just a bit, because in Verilog you don't have this notion of types. everything's just bits, right? So a logic is just a single bit, and then the names are A, B, C, and Y. Yeah, and that's it. And then oftentimes you'll have, line breaks after each of these. You don't have to. If you can really go crazy with the formatting if you want. You can align these in columns and that kind of stuff. But usually it's good to have line breaks there. Although sometimes if I have a small module, I just put the whole thing on one line. Okay, so anyway, so yeah, this code is meant to represent something like this, kind of a black box, right? And then when I start implementing that, I can start putting code in there. So I have two options. I have behavioral SystemVerilog, which is where you define Boolean logic, just like you did in 212, basically. So in this case, I assign the output Y to A or B or C. These look like the OR operators that you use in Java, except they're meant to represent actual Boolean ORs, OR gates. And the assign is called a continuous assignment statement. This is combinational logic, meaning that when any of the inputs change, the output changes right away. You can also implement sequential logic, which has memory in it, and it's clocked. So as the clock goes, you have residual information that's passed from one clock cycle to the next. And that's sequential logic. Hopefully you're familiar with that term from 212. But this is combinational logic. So my point here is that behavioral SystemVerilog is either combinational or sequential logic. It boils down to logic gates and flip-flops, right? The other option is you can put in structural SystemVerilog, and that's what I was talking about with that design hierarchy. So the structural Verilog is where you instance other modules and connect them. You connect their pins. Now, so basically, if you think of this back with that picture I showed on the previous slide, generally speaking, when you look at this design hierarchy, every module in this hierarchy is essentially structural Verilog, because each one of these is comprised of other modules, right? The behavioral Verilog are the leaf nodes. Once you get down to the leaves, the ones that don't have any children, right? The leaf nodes are going to have behavioral, like a full adder is Boolean logic, right? It's, out is A, XOR B, XOR carry in, right? You guys hopefully did one of those in 211, rather. I might have said 212, I meant 211, digital logic. So usually, the leaf nodes are behavioral and everything else is structural. So the bottom line is that most of the Verilog you write tends to be structural, at least in a complex design. Maybe not in this class because they're more simple designs. However, you can also mix them together. So, like for example, in this case, I mix them together. I've got one module and I've got a little bit of a behavioral logic here on this line. I got a little bit of structural HDL on this line, where I instance it in the module. So you don't have to keep them separate. Oftentimes, even if you have a very, a module with a lot of other modules instanced in it, you'll mix in some muxes in there and some flip-flops. So that's a little bit of behavioral logical sprinkling to connect things. Okay? Make sense? Guys with me? Okay. Okay, now let me go back here. So want to point something out. So this is probably pretty straightforward. This is just assigning Y to A or B or C. Obviously the left side of this assignment is the output and the right side is the input. In this case, this might look a little strange because here we've got this inside of Verilog module, we're instancing something called other module. Other module has to have its own Verilog file, where it has its own module line and implementation. My module is the instance name. In general, this is completely useless, the instance name. The only time you'll see this instance name is if you simulate this design, and the simulator will show these instance names, but they don't translate into anything tangible. This doesn't, the name, you can't look at the rat's nest of wires and gates of a deploy design and extract out these instance names. They're gone, right? Because when you convert this to hardware, the whole hierarchy gets flattened out into one mass of wires. right? So all of this design hierarchy stuff is just for design purposes. Likewise, naming modules is also just for the benefit of the designer, right? But you have to give it a name. So I say other module, which is referring to a SystemVerilog module, my module, which is my name. And you'll notice too, like when I show examples, a lot of times I'll just give these kind of nonsensical names, like my module or foo or something, because a lot of cases I don't really care what it's called, right? And then after that, you have the port map. So here's where things can get a little confusing, because in the port map, you have a dot and then the port name. So this presumes that other module has an input called input 1. Well, actually, it has ports called input 1, input 2, input 3, and output 1, right? So these are the ports. And then in parentheses, these are the actual signals inside the scope of this module that I want to plug in, right? You guys with me? So you can think of these as the formal arguments and these the actual arguments, if you're familiar with those terms from programming languages. The idea is that we've got inputs that are defined in the module and then the actual inputs in here that I want to plug in, right? Now, the problem is that all of these things ultimately end up being wires. So really all I'm doing, I just mentioned that the hierarchy is there for the programmer's benefit, for the designer's benefit. What's actually happening here is that this wire A, which turns out to be an input into this Verilog module, so I'm going to take A and I'm going to plug it into input 1, they're the same wire. I'm just renaming it, essentially. So it's called A in here, and then if I drill down into this module, it would be called input 1, but it would be the same signal, the same voltage, the same charge, the same physical signal, right? But there's a renaming that's happening here. You guys see that? That can get confusing because it means the same signal has different names depending on what you're looking at, which module you're in, what your perspective is or what your scope is, right? Different names. Yes?
So ultimately, my module is a Verilog file somewhere else, right?
Yes. Yeah, each module is usually in its own file. It's not always the case, but almost always.
What you're trying to communicate is that as long as my module has 3 inputs and an output, it doesn't matter what the names in that file are? Or are you saying the opposite, that it does matter that they're called?
It matters what the name is for the internal logic. So anything that I refer to as A inside of this design is going to be equivalent in terms of its content to whatever's called input 1 inside of this other module file, right? So the names matter in the way that you use them, right, inside the files, right? They matter in that sense. But when you convert it down to Verilog, all of these names end up just becoming wires that are connected somewhere, right, into some gate.
The point is that when it's actually implemented, the system doesn't have any concept of what the name of these wires is.
Exactly. That's right.
But while you're programming, it does, because it's how the compiler understands to link those two things.
Exactly, and that's how the designer links things together too. As a designer, that's how you define interconnections between components. Yes, thank you. That's a good way to put it. Okay, so yeah, so the syntax is a little weird. It's just something you have to get used to. Now, by the way, one thing that I really don't like about this syntax, this is bad in my opinion, is that from this perspective, when I instance this module, I don't know which one of these are inputs and outputs. Now, it's fairly obvious now because I named them input 1, 2, and 3 and output 1, right? But usually they don't have names like that. So there's no way to tell which of these are inputs and outputs unless I open that file, othermodule.sv, SV being the extension, SystemVerilog file extension. I don't like that. That can be problematic when you're designing things. You don't necessarily know which one of these connections are inputs and which are outputs. Okay. Okay, so let's talk about the continuous assignment statement. So I've restructured this lecture from the way I used to teach it. I used to teach it very sort of conceptual, but now I'm going to just show a lot of examples and try to get down into the nuts and bolts. But I'm going to be switching back and forth between structural and Verilog quite a bit. So if you get lost, let me know. So this is a behavioral snippet of code. I just want to build some gates, logic gates here, right? Now, you guys remember from 2.11, if you did logic gates, you wrote out Boolean logic equations, right? Boolean algebra, and you also showed logic gate symbols. This is another way to do the same thing. It's kind of, and it's nice because it looks more like Java, kind of, right? But you're really just defining Boolean logic. Now, I mentioned that this is a concurrent semantics. So what happens here is that it doesn't matter where this line of code is, because this line of code represents a circuit. And the way it works is if any of the inputs of this circuit change, which is anything on the right-hand side, then it will trigger this immediately and update the value of y. There's no notion here of a program counter or like where we are in the code, at what line of code we're executing. This is a circuit, so when you simulate this, it's treated as a discrete event simulator where basically any changes to these trigger an event that updates that output, right? So basically all of these inputs are linked to that output in terms of their causal effect, right? Any of these change, it updates that right away. So I can take these assignment statements, put them into a module, and I can scramble their order and it won't make any difference to how they behave. You're just literally defining a circuit with this. Okay, now when you simulate this, and I'm actually not planning to do simulation in this class because we do a lot of that in 611. Instead, my plan is to just run these on the FPGA and use JTAG to monitor what's going on. But in simulation and even in JTAG, you end up, when you test this circuit, you end up with this basically a waveform. You end up with what looks like an oscilloscope output where you get this plot where the horizontal axis is time, and then each one of the signals that you're monitoring are plotted there, and then you've got basically two states, 0 and 1, and then you've got these kind of square waves that show transitions between 0 and 1 and 1 and 0. You guys with me? So in this case, A, B, and C are driven. When I say driven, they're being set by someone, not shown here, right? Because this is just showing the output of y as a function of A, B, and C. Somebody is setting A, B, and C. It could be a test bench, it could be some external entity, but somebody's setting these, and whoever's doing it is going through a counting sequence where they're going through every enumeration of A, B, and C, starting out with 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So all 8 combinations are being set on A, B, and C, and then we're looking at the corresponding value of y. So for example, if A is 1, B is 0, and C is 0, then y should be 1, and that should be logically consistent with the Boolean logic. That makes sense? Now you'll notice one thing to note here is that if you want to test an individual case, you generally want to draw a line through, right? And you guys are familiar with these timing diagrams from the protocols that we covered. So they work basically the same way. But you would draw like if you draw a vertical line here, it'll give you one moment in time, essentially, one instant in time, like a snapshot. But generally, you want to stay off of the edges when you do that. You don't want to. You want to usually, whenever you sample these signals, you want to do it when they're stable, because if you do it on their transition, then you don't really know. It's unclear what's going on. Like if you put a line, if you look at this moment in time right here, B is in a state of transition from 0 to 1, and it can be ambiguous. So you generally, whenever you sample these things, you want to kind of be in the middle of the transitions. Okay. So as I mentioned, so what do we do with this? Like, what's the procedure here? Well, as you guys have already done, you start with the SystemVerilog and you pass it to a CAD tool, like Cordis, for instance, or like Synopsys, Simplify, or there's a whole bunch of these CAD tools out there. They're made by these EDA companies, electronic design automation companies. The biggest ones are Cordis, Mentor, and Synopsys, because they tend to buy up smaller firms that make specialized tools, and they kind of keep growing. And then of course Xilinx and Altera, or now it's AMD and Intel, now that they've been acquired, are the two FPGA companies that make the CAD tools. Now you might say, is there any open source CAD tools for this stuff? Not really. There's a few, but in general, none of the free ones, none of the open source ones are sophisticated enough to actually go all the way down into an FPGA, for instance, because the FPGA fabric is kind of controlled by those companies. Okay, but anyway, my point is that you take this and ultimately you're converting, the tool is responsible for converting it to a digital logic circuit. So this is literally, when I say design automation, this is literally automating the procedure that you guys went through in 211, where you would start with Boolean algebra and convert it into a gate level design. The whole point of these CAD tools is they're just automating that. It's just a computer-based version of that. Okay, so another thing that you'll commonly see with these continuous assignment statements is this conditional assignment. So this is a ternary operator that you have in Java and C++, but it's not very commonly used. I use it because I'm used to using it from Verilog, but a lot of programmers don't use this, but technically you can. But it's this ternary operator where basically you start with a condition, you put a question mark, and then you put an expression that the whole thing evaluates to if the conditional was true, and then a colon, and then what it should evaluate to if the condition was false, right? So in this case, you've got S is your condition. If S is 1, then this whole thing evaluates to D1. If S is false, this whole thing evaluates to D0. Now you'll notice that these three things are variables, but they can be constants. Well, the condition's not going to have a variable in there, obviously, but what this is doing is it's creating a multiplexer in hardware. So if you think of this as a multiplexer, S would be the select on that multiplexer, and then the output Y is going to switch between getting the value of D0 if S is 0 or D1 if S is 1. So notice that D0 comes last. See, D0 is on the top of the multiplexer, D1's on the bottom of the multiplexer, but in the expression, D1 comes first because D1 is what you get if S is evaluated to be true, and so if the select is 1, you want D1. Make sense? So you guys, again, hopefully you saw multiplexers in 211. This is a very common little piece of behavior that people will sprinkle in their HDL because multiplexers are the way that you steer signals around and create data paths. Now, you might be thinking, wait a second, why use a ternary? Why use a ternary statement when I could just use an if statement? Because you can't. No if statements are allowed unless they're inside of something called an always block, which I'll get to. But in just the raw HDL, the raw SystemVerilog HDL, these ternaries are really meant to replace an if statement, because an if statement in hardware is a multiplexer. Right? That's kind of the idea. That's the way they're synthesized. And then this is the corresponding waveform. Now in this case, in the previous examples I showed you, these signals were all 1 bit. And so if you declare something as a logic, it's 1 bit. And in this slide, I changed things up because D0 and D1 and D0 are actually 4-bit signals, which is fine too, but they were declared as 4-bit signals, and I know that because I can see 3:0 here, and inside the waveform I also see 4 bits each. Now S is a 1 bit, so S is just a true or false, 1 or 0, but it's controlling 4 bits, how 4 bits flow through the multiplexer. So for example, at this moment in time, D0 is 001, 0001 rather, and D1 is 1111, and my select is 0, so the Y is going to be copied here from D0, which is 0001, because select being 0 is selecting the top input. Yes?
What would happen if a value that was wider than 1 bit was placed in the first operand? Like if S was a 4-bit Y?
You would either get an error, or it would just truncate and use the least significant bit. Okay. Probably you'd get an error, I would think, but sometimes it depends on whether you're synthesizing or simulating. Depends on the compiler and how conservative the compiler is being. But yeah, you have to be careful of that. Usually you would find that when you simulate it if it did get by without an error. But in general, you have to be careful to match your bit widths. Okay, so there's also this notion of internal signals. So in this case, we've got this data type logic, which is just a binary value. It can be multiple values if you want. It can be multi-bit if you want. In this case, it's just 1 bit. And so I've got input logic and output logic. Now, I'm using some shorthand here. If you say input logic A, comma B, comma Cn, I don't specify a type for B or Cn. But the compiler will help us out and assume that B and Cn have the same type as whatever the most recently declared type is. You don't have to do that if you're not comfortable with it. And actually, some might argue that this hurts the readability of the code if you do it this way, but it's an allowable shorthand. Likewise, output logic S, C out, S and C out are both outputs, right? Okay, so I can also declare P and G as logic, as internal signals. You could think of these as you could think of them as local variables, but what they really are wires that are used to connect things internally that are not exposed to the outside of the module. So they're internal signals. Now, normally you use a lot of these kind of wires when you're doing structural structural Verilog, because you implement modules and then you have to wire them together, right? And for every time you wire 2 modules together internally, you have to declare internal signals for that, right? That's the way that you connect things. So it's very common to have these internal signals. In this case, though, I'm not doing structural VHDL. I'm actually doing behavioral VHDL. And so what I'm doing here is I'm assigning P and G, which stand for propagate and generate, and then I use those in calculating S and C out. So this is a full adder, but the full adder is using this kind of terminology from Carey look-ahead adders that does propagate and generate, which you'll know if you took 611 already. But really the only impact of this is that it's just what'll happen is if A or B changes, it'll trigger both these assign statements, which will update P and G, which then will in turn activate these 2 assign statements, because P and G are being assigned here on the left side, but they're on the right-hand side here. So you get kind of a chain reaction, right? You change A or B, that updates P. P changes, it's detected on this statement, and then it's updated in this code. Now you might say, well, what would happen if you took these 2 lines of code and moved them above those 2 lines of code? Would make no difference at all. Because even though it looks like we have this data dependency here where A changes P, P changes S, these changes that trigger these events behave the same regardless of what order you put these in the code, right? So I can, like I said, I can scramble these and it won't make a difference. When you simulate this code, anytime the changes happen, they all happen atomically. So they happen instantly, right? So all of these updates to all these signals happen instantly. If, for instance, you have a circular dependency in your code where you have an event triggers something else and that triggers the original thing and it goes around in a loop, then the simulator will hang. It'll just lock up. Sometimes you'll get a warning that says, event loop has been exceeded. It'll have a watchdog on there and it'll stop. But Model Sim, for instance, the simulator we use just hangs. And then you're kind of stuck trying to find that loop. You have to kind of just randomly, through trial and error, delete stuff and resimulate to see if you can find that loop. So you have to be careful you don't have a loop of events. But in this case, there's no loop. It's just A triggers P, P triggers S, and we're done, right? If this line of code set A, then we'd have a problem. Because A would trigger P, P would trigger A, which would in turn trigger that, and it would go on and on and on. You wouldn't be able to simulate it. Yes?
Is there any useful stack trace tool to look at possible loops if we have that?
Yeah, there's a way. There are some tools. They're generally not easy to use. One tool is you can. Quartus will these designs that I'm showing. Sorry, it's right here. This design actually comes from the CAD tool. So one thing you could do is you can do what they call the RTL view, which will actually generate this, and you can look for loops inside the schematic that's generated from the code. But normally it's so complex it's really hard to read, and sometimes it may even have the loop may even happen through hierarchy. So you may have loops that are formed across the hierarchy, not even necessarily in one, flattened space. So that's one problem. The other thing is Model Sim has has some other debugging tools that are used for that. Not very familiar with them. Sometimes I'll open them and play around, but it's kind of a whole skill in and of itself to trace these things and debug these circuits. Okay, so yeah, I think if you have a combinatorial loop, though, I think the FPGA compilers will actually give you an error and won't compile. But even if they did compile, it would just create it may just create like it ends up, even if it does get by and you put on the FPGA, you end up just having a loop, which is like a ring oscillator. Okay, so now I'm going to bounce back a little bit and talk about SystemVerilog syntax. I just want to mention a few things. So the language is case sensitive, and you might think, wait a second, every language is case sensitive, right? Java, Python, C, C++, everything's case sensitive. Well, no, not necessarily. The reason I mention it here is because VHDL is not. But you guys, VHDL is an Ada or a Pascal-derived language, and it's one of those ones that's not. So you might be confused if you look at VHDL. You'll see sometimes they write it all in caps and stuff, and that's because it's case insensitive. But Verilog is and that's part of the reason, by the way, I switched to SystemVerilog. It's more similar to the languages you already know. You can't have names that start with numbers. You might say, well, who would ever do that anyway? Well, in hardware, sometimes you're tempted to, because if you have a 2-input mux module, you might want to call it 2mux, which would make sense, but it's just against the naming rules. So you have to call it like mux2. White space is ignored, just like all the languages that you guys are familiar with. Comments are // for single line comments, and /*/ for multi-line comments. That's the same as C and Java. And now, one thing that is different and is really obnoxious coming from C and Java, and even from Python, is that basic blocks are defined by explicitly writing out begin and end, as opposed to using left and right brace, or as opposed to using indents like in Python, or even in MATLAB, there's an end, but there's not a begin, because anytime you have a for loop or an if statement, there's an implied begin, if you're familiar with MATLAB. But no, in SystemVerilog, you have to actually write out begin and end, which includes, now where it gets really awkward is, well, I'll point those out when we get to it. There's a few times it gets kind of awkward to put those in, but yeah, so just keep that in mind. Now, obviously, if there's only one statement, you don't need to have a basic block, right? But I'll come back to that. Okay, so here's another example. Here's module AAA, and I've got inputs A, B, and C. And the internal logic just assigns C to not A and B. And so this is a question, I think, from one of my quizzes, example question, or exam, where I say fill in the missing values for the test vectors. Test vectors are just test cases. So in this case, you've got A is 0, B is 0. So what is C supposed to be? What do we expect it to be? Well, we have to work out the logic. If A is 0, then not A would be 1. And then if we AND that with B, which is 0, which would give us a 0, right? So the expected value would be 0. In fact, they would all be 0, except for this second case where A is 0, which gives us a 1 here, and B is 1, which gives us a 1 here. So we'd have 1 and 1. Yes?
I'm having a little bit of trouble interpreting the table. Is that meant to communicate that it's a 1-bit?
Yes.
Number?
Yeah.
What is that?
Yeah, sorry, I got a little ahead of myself. So that's what I was about to talk about. So when you represent those scalar constant numbers, the syntax is number of bits, and then an apostrophe, and then a base, the base that you want to show the value in, which could be O for octal. It's a code, so it's O for octal, H for hex, D for decimal, B for binary. So that's a little different from what you're familiar with too. So for example, if you type 3 apostrophe B101, that's saying 3 bits with a value of 5, which 5 in decimal, which is 101 in binary. If you put 3 apostrophe D6, that's like saying 3 bits with a decimal value of 6, which is 110. Of course, you can use octal. Octal isn't as common, but it's very common to use decimal, hex, and binary. Those 3 you'll use pretty much equally. Octyl is a little different. Now in this case, you have an underscore. You can put underscores in constant values. And this is what this does is it's ignored by the compiler, but as a designer, it allows you to separate values into fields. So because oftentimes you'll have multiple bits, and different ranges of bits will signify different things. Make sense? Okay, but yes, thank you. I rearranged these slides a little bit. So in this table, this is 1 bit and then binary 0 or 1. Because again, the reason for this is just to clarify, there's no standard types. Like in C, you'll have like an integer, which is 32 bits. But in this case, everything is kind of a variable bit number, depending on how you define it. Okay, so now I'm going to jump and talk about another a behavioral construct. So I mentioned to you that behavioral HDL is Boolean logic or combinational Boolean logic or sequential logic, which is Boolean logic that has a memory to it, like a memory, clocked, right? And I showed you the continuous assignment statement, which is the way that you do combinational logic. So how do you do clocked logic, clocked behavior? Well, that's with the always statement. And the always statement is a little kind of got a strange kind of syntax to it. But the syntax is you type always, and then an @ sign, and then you list the sensitivity list. And then after that, your statements, which can either be a single Verilog statement or it can be multiple statements enclosed in begin and end. Now, what's the sensitivity list? That signifies which events should trigger that always block or that always statement. So the sensitivity list is equivalent to when you have a continuous assignment statement, the sensitivity list here is A and B, because any change to A or B will trigger this, even if it doesn't result in a change of C. Right? Like for example, if A and B is 0 and 0 and I change A to 1, so in other words, if I jump from the first row to the third row of this truth table, it actually doesn't change the output, right? But it doesn't matter because that statement will still get triggered and evaluated, right? So in an always statement, you have to list the sensitivity list explicitly there, right? Which is the signals you want it to be sensitive on. Now here's where things get a little weird. You might say, well, wait a second, if we're building circuits here, shouldn't the sensitivity list just be any of the inputs of the circuit always, right? And the answer is no, because sometimes you have signals that are treated as inputs that are not in the sensitivity list because of memory. So sometimes you want things to be able to change without activating the logic, and that's the way that you define the behavior of memory in SystemVerilog. Okay? So think of it like, hopefully you guys in 211 talked about flip-flops or latches. The idea is that you can change the input, but if you don't have the clock, if the clock doesn't change, then nothing happens, right? You just retain the old value, you retain memory for the output. Okay, now the other thing about always statements is always statements allow you to use other constructs that you can't normally use outside of an always statement, like if statements, case statements, and even loops. Although the loops are, if you write a loop, they get unrolled. It doesn't actually loop. But we generally don't use, you generally don't use any loops in hardware. If you have a looping behavior in hardware, then you end up doing it with a counter, right? Basically as a state machine. But you can do if statements and case statements inside these always blocks. When I say case, I mean switch. You might know these as switch statements. Switch statement, case statement, same thing. So just to reiterate this, the only things that are allowed in a module outside of an always statement are structure, which is instantiating modules and connecting them with internal signals or interface signals of the overarching module. Assign statements and always statements. Just it. That's it. It's just three things. There's only three things you can have inside of a module. Why? Because each of these things has a fairly obvious way to generate a circuit. Is the idea. Okay, so let's look at this always statement. So for example, you can write always at a comma b comma c, and then inside the always you can say y equals a or b or c. That is the same thing. Oh, wait a minute. Hold on. Did I skip? Oh, sorry. Let me start with this one. Yeah, it's the same example here. So if you say always at a comma b comma c, you can say y equals a or b or c. And this statement generates a circuit, or it's supposed to be compiled into a circuit, which is the same circuit you'd get if you just typed assign y equals a or b or c. It's the same thing. Now you might say, well, why do they have that weird redundancy? Why is there two different ways to write the same thing? The reason is because these both create combinational logic, meaning there's no memory. But sometimes people like to put combinational logic inside an always statement because it gives you could, for example, do things like build a big if-then-else, complicated if-then-else, or a big case statement, something that would be a little harder to do with an assign statement. But that's kind of that's kind of subjective though, honestly. I can do just about, I would prefer to use an assign for any combinational logic. I almost never do combinational logic inside an always. I only use these for sequential logic, right? But some people don't like to use nested ternary structures for these assign to do an if-then-else, right? Some people would rather do structures and if. It just depends on your coding style. But these two statements are equivalent. That's the point, right? Now, on the other hand, an always statement, the real use of an always statement is to create circuits with memory. But I'll come back to that in just a minute. So one other thing you want to keep in mind here is that an always statement, even if you have a begin and an end, and you have like a sort of a compound always statement with a block, basic block, that always statement gets converted to a circuit, right? In fact, all your always statements become circuits, all your assigns become circuits, right? So there's an important consequence of that. You have to make sure that you don't double drive any signals. Remember we talked about push-pull drivers with SPI, and I mentioned that if you have two SPI slaves and they both have an output that connect to MISO, master in, slave out, you have to be very careful that you don't have both slaves have a conflict on that signal, like where one is pulling to ground and one's pulling to high, because it creates a contention, right? It can create a short circuit, right? That's the same thing that happens in Verilog. In Verilog, everything is assumed to be a push-pull style interface because it's all based on CMOS logic, and the push-pull, the pull-up and pull-down network is the way that CMOS logic is created. So the assumption, there is an implicit assumption with Verilog that we have this push-pull style where if you have two circuits and they go into contention, or one tries to set it to 1 and one tries to set it to 0, that's bad, and it's not allowable, because it'll end up, 1, short circuiting, and 2, it'll put the output into an intermediate state that's not a logic 0 or not logic 1. You guys with me? It'll put it in the forbidden zone, which is halfway between your power supply and your ground voltage, right? So the point is that if you do something like this, where you have an always and you drive Y, and then you have an assign and drive Y, or another always for that matter, right, that drives Y, these two statements are in contention, assuming they're both in the same module, right? These will potentially in contention. I mean, technically for them to be in contention, one has to be setting it to 1 and one has to be setting it to 0. And the way I have this written, that wouldn't happen because they both have the same Boolean equation. But in general, you should avoid this. In fact, I think the compiler, the synthesizer will give you an error here anyway, regardless, because you can't double drive Y. Each circuit, each signal can only be driven by one circuit, by one driver, meaning, a pull-up, pull-down network in the logic. However, you can have a given signal can be an input for a lot of circuits, right? But each can only be driven as an output by one thing. Likewise, check this out. If I have an always where I drive Y, and then I have a structural code where I instance a module that has one of its output ports connected to Y, that's the same thing, because I'm still double driving, because here I've got behavioral logic driving, and here I've got structural logic driving, but they're both driving Y, right? So you don't want to have this happen either. You can have a structure driving it, you can have a behavior driving it, and if it's a behavior, it can be an always or it can be an assign, but just every signal should only have one thing that sets it to 1 or 0, okay? Okay, so let's talk about memory then. Sequential logic. So this is the real strength of an always statement. You can do a thing where you can do always at, and then for the sensitivity list you can say pause edge clock. Now pause edge is a little, I don't actually know what that's called, an attribute, modifier. Pause edge means that normally if you have a signal in the sensitivity list, it means the always is activated on any change of that signal. 0 to 1, 1 to 0, or even like if it switches to a high impedance or a don't know state. But if you say pause edge, this is specifically talking about a 0 to 1 transition, right? And then likewise, there's a negative edge, which is a falling edge. Okay, so what is this for? This is designed for creating flip-flops, edge-triggered flip-flops. And so this is saying, always underscore. Now, notice I have this always underscore FF, which is an optional modifier that was introduced in SystemVerilog that builds in some protections for you as a designer. If you say always at FF, it's just an always block, but it allows the compiler to spit out an error at you if you don't write it correctly as a flip-flop. So you don't have to put the underscore FF. That's an optional thing. Like I said, I try to put it in because it just gives you some extra checks. But basically, it's the same as an always. So in this case, I say always underscore FF positive pause edge clock. Now, what am I doing? I'm setting Q, and I'm setting it to 0 if the reset signal was high, and I'm setting it to D otherwise. So when I have a rising edge of the clock, Q, which is my output, gets D. Now you might say, wait, whoa. Why is Q an output? Where's that defined? Nowhere. It's just because Q is driven inside here, so it's implied to be an output because I set it. I set it inside this always block, so that always block now gets control of Q, right? That's an output. D is an input, not because I specified it as an input, but because it was used as an input in the code, right? It was used on the right-hand side of an assignment statement. So Q is an output based on how I used it, D is an input, and all clock is an input, and reset is an input, but I can change reset and I can change D without anything happening because this thing won't do anything until it sees a rising edge of the clock based on the way it's written here, right? So this creates a flip-flop, rising edge triggered flip-flop with a synchronous reset, meaning that if the reset is high and I get a rising edge of the clock, I'll reset the output to 0. This is a 4-bit too, which I only know because I have a 4 apostrophe here. And it's implied that D and Q are declared as 4-bit values. Everyone with me? So this is a little snippet, but created a 4-bit flip-flop. Now you might say, wait a second, I thought flip-flops were 1-bit. Well, yeah, I mean, when you learn about them in your digital logic, usually they're presented as 1-bit, but if you have 4 of them in parallel as a group, that becomes a 4-bit wide flip-flop, just like we did with the MUX earlier. Guys with me? You can do other stuff too, like you can add a pause edge reset in the sensitivity list. This will do the same thing, except this will end up becoming an asynchronous reset, meaning that if the reset goes high from low to high, it'll instantly reset Q without waiting for the clock. And you might say, wait, should we be, which style should we use? Synchronous or asynchronous? That's just up to you. Usually doesn't make a difference, to be honest, but textbooks always make a big deal out of that. This one has no reset at all. This one has an enable. So this one has an asynchronous reset, and it has this additional input called enable, which it'll basically not do anything even on a rising edge of the clock unless enable is high. So you can add little features to your flip-flops based on how you use it. Now this is a little confusing because, as I mentioned, it's not explicitly shown what the inputs and outputs of this circuit are. They're all implied based on how they're written and the sensitivity list. So that's part of the thing that's kind of strange, is that it's not like you're just grabbing a block from a library of components and saying, I want a rising edge flip-flop with asynchronous reset and an enable, and I want it to be 8 bits wide, plump it down. This is just, you're getting that through the description on the code. Make sense? And then you can do things like this as a counter. So this is really neat. This thing will take Q, and it uses it as an input and an output. And it'll end up creating a loop, and it'll count. Now you might say, wait a second, I thought you said loops were bad. Loops will hang the simulator. Only combinational loops. But in this case, we have Q and Q, but because it's inside a clocked always statement, it effectively breaks up that loop with a flip-flop. So basically every clock tick, it'll increment by 1. But in the meantime, when there's no clock loop, there's no clock edge, then the loop is broken. There's no loop, right? Guys with me? And the nice thing about edge, by the way, the whole reason we're using edge triggered is because the edge is supposed to be a really short amount of time, right? It's the rise time of the clock. Not the time it's high, not the period, not the duty cycle, but the rise time, the time it takes to charge the wire from 0 to 1, right? That's a short amount of time. So that's so short that it doesn't leave any time for this actual combinatorial loop to be established, because it's an instant. You know, it's like it goes from 0 to 1 and it increments Q. Okay, so that's how you use an always statement as a counter. So I want to go through an example here, and hopefully I have time to do this. If not, I'll continue it next time. So let's jump into Quartus here, and I'm going to create a new project, and we're going to do a new Quartus project, and I'll just call it test design. This is the same process that you guys went through for the lab. I'm going to create it, go next. I'm going to choose the FPGA. Package is FPGA, pin count 780, speed grade 7, and the size is 115. So 115 C7, hit next there, finish. Okay, so I got a new thing, and then now I'm going to create a file for this. So the project's called test design, and by default, the top level module is supposed to be called test design too. Now you can change that, but I'll just to make it easy, I'll say new SystemVerilog HDL file, and I'll just say module test design. And okay, now I need inputs and outputs. Okay, now the question is, what are my inputs and outputs? Remember that because this is the top level design, my inputs and outputs have to be physical pins. So I'm going to use input clock 50, and these have to be named exactly this to match the pin mappings. And then I'm going to have an output. Actually, I'll have an input here called key, and I'm going to put 3:0 there before that. Now, this is another thing that I hate about SystemVerilog, by the way. In every other language, if you have an array, you put the array bounds after the name. But in Verilog, you put it before, so input 3:0. They do that because it's part of the type. It's a 4-bit signal, so that's why they went on the left. They consider it part of the type, right? It's not really an array. If you make an array in Verilog, then you would additionally put other indices after the name. Okay, but anyway, still, always hard to get used to. And then I'll have an output called LEDG, which is going to be 8:0, which are my green LEDs. And see, I just screwed it up. I just did it after. Look at that. Put it before 8:0, and that's a bracket, not a parenthesis. And then, don't forget your semicolon after the module line. And also, I forgot logic, so I'm going to put that in here as well. You don't always need that, but if you drive any of these with an always statement, like if you set any of these with an always, then you have to have the logic. So I just always put logic there. I think it's just easier that way. And then end module. And there we go. Okay, so I'm gonna create some internal variables called logic A, B, C, and Y, just like I showed in the examples. And I'm going to assign Y to be not A or B or C, which is like using a NOR, a 3-input NOR gate. Okay, now normally I would be able to just run that as it is. However, if you synthesize this design, these A, B, C, Y, and this assign will get optimized out, because they're not connected to the real world. They're not connected to the pins. And there's no way to stop the compiler. I've never found a way. People on the internet claim, oh, you can put pragmas in, and there's no way. Unless you connect the inputs and the outputs to pins, the compiler will never compile them. They'll be blown away. So to get around that, I'm going to assign LEDG bit 8 to Y. LEDG8, by the way, is the 9th green LED. It's actually in between the 7 segment displays. You guys were only using the 8 green LEDs over here, but there's actually a 9th one. Now you might say, well, wait a second though, what about A, B, and C? Who's going to set those? I'm going to set it with a counter. So I'm going to say always at pause edge clock 50, because that's my clock in this case. And I'm going to say A, B, C equals A. And I'm going to use this assignment statement. I'll come back to that in a minute. A, B, C plus 1. Okay, so first of all, this brace is just doing a concatenation. So it's saying treat these 3 1-bit signals as one 3-bit signal. And I'm adding. And notice I have, now you might say, wait a second, can you add 1 bit to 3 bits? Yeah, that's fine. That's not a problem. In fact, that allows it to synthesize, or to simplify the adder, actually, because you only end up having a 3-bit and a 1-bit input to your adder. You might say, wait a second, what about reset? Do you have a reset in there? No. Because when you power this up, they'll come up as random values, and then they're just going to count from that random starting point. So I'm fine with that. I'll let them just, they'll be randomized when they come up, but then they'll just keep counting and go from 0 to 7 and roll the odometer back to 0. And then these guys will be used to calculate Y, which then will ultimately go out to the green LED. So this thing will drive its own inputs, and it'll go through a counting sequence. Okay, now I'll save that, and I have to still import these assignments, unfortunately, which I think are on, if I go up a level and go to DT, I think, yeah, DE2 pin assignments, or I get that imported, and we should be good to go. Okay. So now I'm going to click, I don't know if you can see that in the back, but there's 3 different ways you can compile this. I'm going to use the start analysis and synthesis. It's like a part-way compile. It doesn't go all the way to a SOF. And I'll tell you why here in a second. So I'm going to click that, and this should be a quick compile because it doesn't do the whole thing. But it's still going to be kind of slow because I'm running this on a laptop in a virtual machine. But okay, so I'm going to get that going. So what I want to do next is, in order to test this, I can't look at the green LED because it's going to be running. It's going to be counting through all 8 input combinations, but it's going to be doing each combination at a 50 millionth of a second. So obviously it's too fast to watch, but there is a solution to that. The solution is to use a tool here called Signal Tap. if you go to Signal Tap Logic Analyzer, you click that. Okay, this thing is some of you might have heard the term logic analyzer. Usually that refers to a bench instrument. In fact, we have them in the lab, the big boxes that are on top. But this is a virtual logic analyzer that we can do through JTAG. So the way you use this is you do a right click here and here, and you say add nodes, which are things you want to monitor. And you select the signal here to the type to pre-synthesis, and then you hit list. Okay, now when I do that, you can see I've got A, B, and C and LEDG there. So I'm going to click those, and I'm going to move them to the right side. And LEDG, I just want bit 8. I don't care about the other bits because I'm not even driving them. So then I'm going to hit insert and close, and I've got them listed. And then I have to go over here and specify my clock for the capture. So the way this virtual logic analyzer works uses the clock to record the signals when a trigger happens, and then it reads it out through JTAG. So I'm going to say list, take clock, move it over, hit OK. Now I've got the clock. I'm going to record 128 samples, and then I'm good to go. So now I'm going to run this. I have to recompile to put in these probes. It says the signal tap file has been modified. Do you want to save? Yes. I'll save it as STP1. Do you want to add the file to the current project? Yes. So what that does is if I go over here to the files thing, you'll notice now that I have 2 files in this design. I have my SystemVerilog, and I've got this STP, which is just a list of my probes that it's going to put in. Now you might say, where's the pin assignments file? Well, I never added that. I just imported that. If you import, it just reads it. But if you actually add it, then it lists it here, right? That's the difference between adding and importing. But I just have the 2 files now, and I have to resynthesize this to make it work, to put all the plumbing in to be able to read those virtual logic analyzer out. Okay, this will take a little longer because I have to do a full compile. But once it's done, I can deploy this design on the FPGA, and then I can watch it, what's going on internally with these probes. Now, the downside of this, by the way, is that every time I want to monitor a new signal, I have to go in and add them the way I showed you and recompile it, which takes time. But if you're doing a simple design, it's usually not too bad. So it's still going. Oh, you know what? Hold on. I'm sorry. Time out here. Sorry, I'm going to stop it. I forgot one thing I want to do. I do want to put a reset in here because I brought that key in. I'm going to add a thing here that says if, actually I'll put a begin even though it's still not technically necessary. Begin, and I'm going to say if key of 0, the rightmost key, if that equals 0. So when I push a key, it's 0 because they're active low. If it's 0, I want to reset. So I'm going to set these to be 3D0. 3B0, it doesn't matter. And then say else. I want to do that. And then end. Okay, there we go. And the end should not be indented. Or it should be, but only one level. There you go. So I've got always at pause edge, clock 50, begin. I've got a begin and end here for the always block. The if, I don't have begin and end just because there's this one statement in there each. So if key of 0 is 0, because again, if you push a key on these boards, it's 0. If you release it, it's 1. Okay, sorry about that. I'm going to, actually, I want to recompile it, but I want to do it from Signal Tap. So yeah, I'll hit compile on Signal Tap. And that should trigger the compile in Quartus. Okay, it did. Okay, yeah, so the idea, and by the way, the reason I put that in there, even though I didn't need to put a reset, is it gives me something to trigger on. So what I'm going to do is I'm going to set a trigger condition in the logic analyzer that says, when I push the reset and then release it, when I release it, the reset signal will go from 0 to 1, because that's 1 is the not pushing state, right? And then at that point, it should increment that counter, and then I can watch it. And you know what? I also forgot. Sorry. Oh, good. I got an error anyway. One other thing I want to add here to Signal Tap is I want to add the keys there too. So I want to add a node, and I want to add key of 0. Yeah, let me add key of 0. Okay. All right, now we're good. Key of 0. That because you need to have everything in there you want to view or trigger off of. And what was the error? I didn't see it. Let's go ahead and try running that again. All right. I think I might just have time to pull this off. I've got 4 minutes. So like I said, every time you modify the STP file, you have to recompile because it requires actual logic to be put on the FPGA to support the virtual logic analyzer. And you'll see there's a warning message here that says LED bits 7 down to 0 have no driver, which is intentional. I'm not driving those because I'm only driving the LED G8. Sometimes you'll see meaningful messages here, but usually not. So in this case, it's just saying it's finding one design unit, including one elements, and so on and so forth. This is just one file, but the probes add some additional complexity. But in general, I'm using very little of the FPGA. This is a very small design, and even then, it still takes a while to run this. But this would be much faster in the lab. Okay, synthesis is done. Now it's doing the fitter. That should be fast. Oh, by the way, too, I did not add the constraint file. So technically, this CAD tool does not know what speed the clock is supposed to run at. So it's kind of doing the fitting blind because it doesn't know what sort of performance I'm expecting. But since this circuit is so simple, it's just a counter. I'm sure no matter what it does, it'll easily run at 50 megahertz. With you guys, when you guys do your platform design, there's the whole NEOS processor, and it's more important to tell the tools that you're expecting a 50 megahertz clock period. So it has to guarantee that performance, or else, fail. Okay, assembler now. This is generating the programming file, the soft file. And come on, there it goes. That's done, 90%. All right. Timing analysis, which I'm surprised it's even doing because there was no constraint file, as I just mentioned. Not sure what it's timing against. And then the EDA netlist writer, which is the actual conversion from the netlist to the soft programming file. All right, and that should do it. Okay, so then if we go back to Signal Tap and we select the USB blaster up there, and okay, I'm getting the no device selected thing. Setup, scan. Oh, there we go. Scan chain. Come on, find it, find it, find it. See, this is that same issue we always have with the JTAG, which it can be. Have any of groups you guys having trouble with that programming the FPGA? You've been having some issues. It's so funny. Like some machines, you can just program it no problem, and then other cases, including this, there's these programming issues. When I did this in my office, I did have this problem, and I had to restart, and I came back and it fixed it. I'm not sure if I'll have time for that now, but I will. I can finish this up next time. I'll just give it one more shot because if it works, it'll be fast. But basically, you would program it, and then you just hit the run button in Signal Tap, and it'll actually show you what's going on with those signals that you have probed. Okay, well, it's okay. I'll finish this next time, and actually, it won't be for 2 weeks because next week we'll be doing a review on Monday. You'll be taking your exam during that week and demoing your labs. So in 2 weeks, we'll come back to the SystemVerilog stuff. Whoop, there we go. Hold on. Wonder if this will work now.
The week after is spring break.
Oh, is it? Yeah, but we've got. Oh, is it? Well, in that case, it'll be. Yeah. Then, and if that's. Yeah. Then in that case, it'll be 3 weeks. Okay. We'll see you then.